Okay, we come now to Mr. Kluschak. The subtitle of the presentation is Multi-Parameter Average Strain Density Factor Criterion applied on the D-material notch problem.
Thank you, Mr. Chairman. So my name is Jan Klusak, and this is the title of my presentation. So I will talk mainly about stability criterion of bimaterial notches, and the stability criterion will be derived on basis of average strain energy density factor. I would like also to thank to my co-author, Ondřej Krepel, and we are both from the Institute of Physics of Materials from the Academy of Sciences of the Czech Republic. So first, the outline of the presentation. After short introduction, I will talk about stress distribution near sharp and bimaterial notches. Then I will introduce multi-parameter average strain energy density factor criterion. I will show the application on numerical example and final conclusions. So first, the introduction and some motivation. You know that composite materials often occur in engineering structures and also in everyday life. And you know that there are many of geometrical and material discontinuities. This is a picture of a cheesecake. This cheesecake was made by my wife, and there are also many of geometrical discontinuities and material discontinuities, and even in this cake occur cracks. So I have great motivation to solve forming cracks in composite materials and to study bimaterial interfaces and so on. Well, how we model sharp and bimaterial notches. This is the model of bimaterial notch. There are two material regions, material 1 and material 2. These regions are characterized by angles gamma 1, gamma 2, and gamma 3. Materials are characterized only by their elastic parameters, Young's modulus, Poisson's ratio, and finally I must say that we consider only plane strain or plane stress conditions. We also assume perfect bonding on the interface. And as to the sharp notch, we consider sharp notch as a special case of bimaterial notch, where material 1 equals to material 2. The stress distribution near the sharp notch, there is singular stress distribution similar to crack. The stress distribution can be described by this infinite series. We use the sum of n terms. Each term consists of hk, which is generalized stress intensity factor with these units. Then there is r powered by minus pk. Pk is the exponent of stress singularity. If pk is between 0 and 1, the stress terms are singular, while if pk is below 0, the singular term is, the stress term is non-singular. Sometimes we use also eigenvalue lambda k, and the relation between pk and lambda k is stated here. Finally, there is also shape function f. It is angular function which depends on polar coordinate theta. crack formation occurs in the tip of the bimaterial notch or sharp notch. In order to describe stability of the notch, there are many approaches, and in this paper I would like to present multi-parameter criterion using average value of strain energy density factor. Why multi-parameter criterion? The reason is because some cases of bimaterial notches or other singular stress concentrators like bimaterial inclusions and so on, they need more than singular terms, also non-singular terms, in order to describe stress well. So stress description, including non-singular terms, requires also stability criteria, including non-singular terms. So first, the basic definition of strain energy density factor. It is given here. Strain energy density factor is independent of R for case of crack, but it depends on R for generalized stress singular concentrators. From this reason, we use average value over certain distance d, and the average value is defined here. And this quantity will be used to define stability criterion. So, as we consider plane problems, for the plane problems, strain energy density factor can be obtained by means of stress components in this formula. And after substituting the stress components and the integration according to the previous relation, we get the relation for average value of strain energy density factor. This is not that difficult. There is some outer sum and inner sum. We sum over K and L subscripts. There is also function U, which depends on shape functions from the relations for stress distributions. And these two terms are gamma K1 and gamma L1. They are ratios of generalized stress intensity factors. So gamma K1 is HK over H1 and gamma L1 is HL over H1. So we have the relation for average value of SEDF. By means of this quantity, we can determine direction of crack initiation. We are looking for the minimum of strain energy density factor, or its average value. So these two conditions must be met. The first condition is written here. After derivation, we obtain this relation, and based on this relation and based on the knowledge of the ratios of H factors, we can get the crack initiation direction theta 0. The subscript M means that we must look for the crack initiation direction of in each material region, and we consider the material 1, material 2, and also the interface, the direction of interface. So it was the crack initiation direction, and when we want to get crack initiation conditions, we must have a critical value of strain energy density factor. It originates from case of crack. For case of crack, the critical value of strain energy density factor depends on K1C fracture toughness. here is the critical value for general singular stress concentrator for the case of bimaterial notches, and when we equal these two values, we get the critical value of H factor. It depends on fracture toughness of particular material region. This critical value should be evaluated also for material 1, material 2, and for the interface. Finally, we take the minimum when we calculate the critical values of H factor for these three materials, or material 1, material 2, and for the interface. We take the minimum of these three values and we compare them with the H1 value. And if H1 is lower than the minimum of these three values, a crack will not initiate in the bimaterial notch tip. For better interpretation of results, also critical applied force can be derived, and this is this relation. Well, I will show the approach on a numerical example. We have this aluminum epoxy configuration, 3-point bending loading. There are dimensions. Applied loading was 100 newtons, and as the value of averaging of the strain energy density factor, it was chosen 1 millimeter. There is average strain energy density factor distribution. You can see the yellow points. This is SED factor calculated by means of singular terms only. The blue points are SED factor calculated by singular and non-singular terms. You can see that in the region of minimum there is about 25% difference. So it is the minimum of SEDF. These are the values on the interface, and this is the distribution in aluminum region. So the inputs and results. The main input is fracture toughness of epoxy, aluminum, and the interface. The values are here. Then there are values of critical H factor for epoxy, aluminum, and interface calculated by means of singular terms only. There are the same values calculated by singular and non-singular terms, so by using of multi-parameter criterion of stability. And the critical forces are stated here. So the lowest critical force is for the case of interface, so we expect crack initiation into interface, and you can see that using singular parameters or multi-parameters criterion, the difference is about 8%. So let me conclude. I have shown the stress field near bimaterial notch tip described by singular and non-singular terms. Also multi-parameter SEDF criterion was shown. And the absolute values of average SEDF gained from solution without and with non-singular terms, the difference was about 25%, and this have led to about 7.5 difference in the values of H1C and also of the critical applied forces comparing results with and without non-singular terms. This is all from my side, and I would like to thank you for your attention.